Okay, everyone, we're going to look at number 9 in section 2.4. We have this piecewise defined function for values of x not equal to 2. It's equal to this expression, which is good because this expression is undefined when x is 2. But for when x is 2, we're going to have the output just to be equal to 6. We're going to determine the points at which the function is discontinuous and state the type of that discontinuity. So first of all, what's the value of the function at 2? It's equal to 6. And for any value other than 2, we know the function is continuous because this expression here, x squared minus 4 divided by x minus 2, is continuous on its domain. And what's its domain? Its domain is all real numbers except for 2. So for every real number except for 2, the function f is continuous. So the only question is what's happening at 2. We know the value of the function at 2 is 6, right? But what's the limit, right? Because remember, for it to be continuous, the limit has to exist, the value of the function has to exist, of course, and those two values have to be equal. In other words, the limit as x approaches 2 of f of x must be equal to f of 2 must be equal to 6. So the question is, what is the limit as x approaches 2? Well, if we're looking for the limit as x approaches 2 of the function f of x, in the limit process, we're guaranteed that x is not 2. So we're clearly using this top formula, right? So we're looking at the limit as x approaches 2 of x squared minus 4 over x minus 2. If I plug in directly, I get 2 squared is 4 minus 4 is 0. And on the bottom, I get 0 as well, right? This is indeterminate, right? Form. Okay, doesn't mean the limit doesn't exist. I can find the limit numerically. You could just plug in values closer and closer to 2, like 1.9, 1.99, and so on into this expression. But we could do some simplification. We could do it algebraically as well, right? Factor x squared minus 4. And then I have that common factor of x minus 2 that we expect. And the limit now becomes as x approaches 2 of x plus 2, and this is continuous at 2. I can plug in directly and we get 4. So notice the limit as x approaches 2 of the function is 4, but the value of the function is 6. Since these are not equal, the function is not continuous. Okay, it's not continuous. It's discontinuous at x equal 2. Now, what type of discontinuity is this? This is a removable discontinuity. In other words, the value of the function at 2 is 6, so there's that point. The limit, so we're approaching this hole, which has a y-coordinate of 4. So the value of the function, 6, is not equal to the limit. But this is a removable discontinuity when the limit exists, but the value of the function is something else. And I can fix this by basically, if I just redefine the whole function here, from 6 to 4, right? In other words, if the output is 4 at x equal 2, that would basically fill in this hole, and the function would be continuous at for all real numbers. Okay, so I hope this explanation helps, and if not, please let me know.